Welcome back. This time we're going to check out some graphics programming. More specifically, I want to recreate the Mandelbrot fractal, and I want our result to be saved as a file on disk. And for the saving of files, I will take help of some Java classes that are specifically created for this. In Java there is a class called image.io that we can use to write images to disk. So if we have an image and we want the resulting file to be of type PNG, and we write it to an output stream. So file stream in Java is created by saying file output stream, and we need to give the file a name. Let's say result.png, and we use the use function, which will ensure that the file is closed and cleaned up when the program is finished. And this is the out stream. And our image, I will also use a Java class called buffered image. And let's create an image of size 32 times 32 with the type RGB type. And if we now run our program, we should get an image on disk here. Let's open it. Right now it's a complete black image because we have not created any content on it yet. Now let's try to put some pixels on our image. There is a method called setRGB, so we can put a color at any pixel. Let's say X value 5 and Y value 5, and make that pixel of the color FF, which will be a blue pixel. And we run this, we get the blue pixel at position 5.5. Okay, so let's extract this into a method that says create image content. And I also want to make this an extension method. So we say convert parameter to receiver. Then this is an extension method on our image. And if we were to say 0 until width, we can call this our X values. So if we now put this color on all X values, we should get a blue line across the whole image. And let's do the same for Y values, but this time to the height of the image. This would give us the Y values. So if we run this, we got a completely blue image. No, need to put in the Y value. There we go, a completely blue image. And if we make this image a little bit larger, like 512 times 512, run it, we get a larger image. Now we can play around a little bit with this. Instead of having a blue color here, let's say X, and run it, and then we see it starts at completely black at 0 and goes up to completely blue at 255, and then it restarts. We could actually do something like plus y, and we will get diagonal lines. But if we instead were to say that we shift the y value with like 16, it will mean that we put this y value into the red part of the integer that we return, and we get this nice image. We do get this repeating pattern because colors go from 0 to 255 and then they start over in this image, and our image is 512, which is twice that size. But I would rather using normalized coordinates that have 0, 0 in top left, 1, 1 in the bottom right. So we need to scale our x value. So if we divide our x value with the width with -1 to double, then xn will go from 0 to 1. And if we now use that in our color calculation instead, we have to multiply it by 255 to get it back to color space, and then make an integer of it so we can use it as a color. And now we see it stretched out horizontally. Let's make the same thing in vertical, the y. So we divide y with height -1, and we do calculations in doubles, and then we can do the same here, times 255 and to an int, and it should stretch out in vertical. We need to use it, of course, like that. And I know I want to make this reusable method that we can use for multiple graphic projects in the future. So, and we look at this part is the actual part that calculates color given a x and a y value on the image. So if we were to have a function of the type double double, that is our x and y value, that would return an integer that it's our color. It could actually move our calculations here up into here. That is our xn and yn. And then instead of this, we can just call f of xn, yn, and it should still render the same image. And now we can make this a method and call it for each pixel, maybe. So we have abstracted out how we traverse over an image and don't have to look at that anymore. Just think about how we want to create our image content. I also want to abstract out how we calculate our colors. So let's say that we were to have a color red, for example. I would like it to be written like this. For example, RGB 1.0, 0.0, 0.0. So we have full red, no green, and no blue. So to make this happen, we need a class RGB with a red component, a green component, and a blue component. And if we were to put that in here instead, we want a way to convert our RGB class into an int. So let's just say value. So we create a property called value where we do the actual calculations from RGB components into an int color. And we do it by saying red component times 255 as an int, and I shift it 16 bits to the left. And if we render this now, we got a completely red image. And if we say that we want some green in it, we also need to add that part. And shift that by 8 bits. I do think this is the application, so I would want to make it a method. Let's say function to color component, where we have our color component as a double and our shift number of bits that we want to shift it as an integer. So we can take this calculation, color, and shift bits. And now we should be able to use it. Let's say that we want the red component shifted by 16 bits. And our green component and our blue component shifted by 8 bits and 0 bits. And if we run this now, we should get a color that is fully red, fully green, and no blue, which results in yellow over here. And we can now try it out again by saying RGB, and we do X as our red component and Y as our green component, and maybe 0.5 as our blue component, and we should get an image with looks like this. So now we can paint colors, And let's try to create our Mandelbrot function. So we say our function Mandelbrot that will take x position and y position, and it will return an int that is our color. The Mandelbrot fractal use complex numbers, and the formula for the Mandelbrot looks something like this, that we have a starting value c, that is a complex number, where the real part is the x value and the imaginary part is the y value. And we have a starting z, that's the same as c. And then we iterate, and for each iteration we square our z value and add our c value. This don't compile because we don't have any complex class. So we create it, complex. We have a real part, type double, and an imaginary part of type double. And we want to be able to square complex numbers. And we create a function for that will return a complex value. Return complex. And squaring a complex number will give us a real part, that's r times r plus or minus I times I, since an imaginary part times itself will result in a negative value, and the imaginary part will be 2 times r times I, the imaginary part. And we also see we need a plus operator, and plus is a little bit easier. It's we just add the real part with the other real part and the imaginary part with the other imaginary part. And we want to iterate this up until a limit. Have a max limit. Let's make it 200 maybe. So we do this 200 times, or we will return the color 0x0. This is completely black. Let's call this function instead of this old color function. So we can call our Mandelbrot function in here for each pixel, called Mandelbrot function. If we run it right now, get the complete image, because we always return 0. But we want to, in each iteration, check that if our complex number have grown, so that if the real part and the imaginary part have grown to be larger than some limit, let's say 100, let's just return the color red, full red. We see something that might be a part of the Mandelbrot set. This is actually the lower right part of the Mandelbrot set. We have 0.0 here in the middle, but we want to see also the negative parts of the axis. So to do that, before we start calculating, we need to scale our view. So, and let's say a scaled x we can calculate by, let's say that we want to start at left x equals to negative 2.5 and go to the right the positive 2.5. So the scaling is done by taking our x and multiply it with right x minus left x, and then add the left x on it again. And if we use this scaled x in our calculations, we get a skewed half of a Mandelbrot set. So we need to scale it also in the y-axis. And we do the same calculation. We just use bottom and top instead. So our scaled y use bottom y and top y, and we put that in our calculation, and we get something that we might recognize as the Mandelbrot set. We might recognize this calculation. It's actually the linear interpolation, so let's call it that. But I want to refactor the signature of this a bit. I want to put this last, this first, and I want to call this start and end value. So this is an interpolation method. And also let's move this to a method and call it scale, because now I can, let's duplicate this. So we can have a zoomed in variant of our scale maybe. So what happens if we instead show from negative 2.0 to 0.0 in both axes? It would show only the top left part of our fractal. If we run it, we see our top part. Let's zoom in a little bit more to this maybe. Yes. And let's try to figure out some color scheme to use for this. This is the part where we decide which color to use for our fractal. I will extract it to another method. Call it Mandelbrot color, and I want our color to be dependent on our current set value and our current iteration, which is here. And now we can try to figure out how we should color our fractal. Naive way could be to just say, instead of 1, we say our current iteration. And it needs to be double. Let's divide it with 200, which is our max iteration. If we paint this, nothing happens. We get something that looks quite cool actually. So this is one way to color it, but I think we can do better. What if we do something I have experimented some previously and figured out one way to do it? If we do square root of our current iteration minus log 2 of log 2 divided by 2, and inside here we have ZR times ZR plus ZE times ZE. Well, if we were to paint this instead, we get something that repeats from black into bright white, restarts at black and goes to bright red, it should be. And we can actually look at it if we take away our zoom here and look at the whole thing. We see some coloring. What I want to do now is take each gradient from black to red, and make it its own color. And I want to pick colors from a color table. So let's make a table of colors. That's an array of RGB values. So if we want, for example, go from one completely white color to something, maybe something with a bit red in it, and maybe to something I'm just coming up with values here, something like this maybe. So if we here instead would make RC and take the reminder of division of colors dot size and use that as an index into a color table. We get something that looks like this. It goes white, red, blue, white, red, blue. Let's zoom in a bit. White, red, blue, white, red, blue, and so on and so on. This is nice, but I want to have going as a gradient from white slowly to red and slowly to blue and slowly back to white. And to do that, I will go from the color at the index 0 and going to this +1, but this will fall out of the table, kind of, so we need to again take the reminder of this. So if we instead use index 1 here, the colors should shift one step. So it's red, blue, white. So now I want to do an interpolation between color at index 0 and color at index 1, and the value I want to interpolate with is C minus floor of C. And this method don't exist, so I will create it. So we have our color 0 and our color 1 and our interpolation value. And we interpolate by interpolating each color component. So C0 point red with C color 1 point red with the value of V. And we do it for the green and the blue component as well. Green, blue, green, blue. We look at it and we get nice gradients from white to red to blue and back to white. Let's zoom out and see the whole thing. It starts at white, goes to red and blue, and I actually want to paint this border or everything that's outside of the first white as white, and we do that by taking this value just let's call it if v is less than 0, return colors index 0. And if you run it, it will take the first color in the table and put it on the outside here. I think this is nice. Let's try to zoom in a bit and zoom in even more than this. Let's say 0.6. I think this might be close enough. Yep. And now I leave it up to you to play around and figure out your own color schemes around this. Thank you for watching.